Okay, can you hear me? Okay? All right, good. So today I'm going to teach you something. That's what I do here at the University of Iowa. I'm a professor of chemistry, and I like everybody to go away learning something new from my presentation today. I'm going to step back a little bit from some of the things that Betsy Stone talked about and Dan Reed, and tell you about a part of the atmosphere that you may not know much about. In particular, I want to tell you about the chemistry and the impacts of atmospheric particles and what role they play in the Earth's climate. So how many people know much about the Earth's atmosphere? Probably all of you know a little bit, is what I'll say. But what you probably know is that the Earth's atmosphere is composed mainly of gases, including things like nitrogen, N2, which is the predominant gas in the atmosphere. Oxygen is next, but then we also have these other gases, including things like CO2, carbon dioxide. There's been a lot of discussion of carbon dioxide because it's a greenhouse gas. Water is also a greenhouse gas, water vapor, not water that you drink, but the vapor above that. We have things like argon, so we have many different types of molecules, atoms, radicals, species that are present in the atmosphere. They're all in the gas phase. They're hitting us, all of them are hitting us. So if we were to be a molecule, we would have, you know, banging down on us. That's happening all the time. They're really small, you can't see them. Whoops, I ruined the whole talk now. Excuse me for that. Oh, there we go. Okay, I won't do that again. Okay. And currently, most atmospheric chemistry and climate models really only consider gas phase chemistry and gas phase photochemistry. Photochemistry is chemistry initiated by the sun. Okay. But what about the particles? The particles in the atmosphere also play a role. These particles are called aerosols, as well as particles. They're liquid and solid particles suspended in air. We know that in the stratosphere, so here's the Earth right over here. It's not as pretty picture as Dan Reed showed, but if we go out 10 kilometers, that's the troposphere. That's the region closest to the Earth's surface. Higher up, 40 kilometers, that's the stratosphere. We talk about things like the ozone hole occurring in the stratosphere, and that was due to chlorofluorocarbons. But what I would tell you is that ice particles in the stratosphere also play a role in ozone depletion. And we know how that works. We have the reactions occurring between chlorine inactive species to chlorine active species, which gives rise to reactions that deplete ozone. But here, closest to the Earth's atmosphere, namely the troposphere, we have a lot more types of particles besides just ice particles. We have black carbon or soot, we have sea salt, we have organic, we have mineral dust, we have aqueous aerosols, but much less is known about them. So how do these particles get into the atmosphere, and what do they mean to all of us? There's a number of different ways. Some is just simply particles are ejected into the atmosphere through a number of different mechanisms. Sea spray is just from wave action. So if you walk by the beach, whether you're in San Diego or the Jersey Shores or wherever you're walking around, you'll see the ocean waves. Well, that actually gives rise to particulate matter in the atmosphere. Mineral dust is ejected into the atmosphere. There are a lot of dust storms occurring throughout the world in many of the desert regions, Asia, which are in Asia and Africa, but they can also happen in Phoenix or even in Iowa. And what happens there is that you have these windblown soils emitted into the atmosphere. And you can think about this as a natural emission, but what I will tell you, and probably some of you may even know this, is that there's some influence from anthropogenic activities, from man activities. So if you overgraze a land, you make it dustier, and so you can get more mineral dust into the atmosphere. We have volcanic ash. We have things like soot. You ever follow a CAN bus, right? A CAN bus stops, then all of a sudden it starts up, a bunch of black smoke. I hold my breath. Okay, and then that's black carbon getting into the atmosphere. And so these particles get out. There's another mechanism. It's called secondary particulate matter. People here in the audience are experts on this, but basically you can have gases in the atmosphere coming together and condensing to form a particle as well. So there are several different mechanisms, and some of these gases are gases that are emitted through industrial processes, and so these are particles that can get into the atmosphere, but some of them are also naturally occurring. Now, these particles in the atmosphere, I sort of listed a few. Sometimes and oftentimes they're mixtures of each other, so it makes kind of a complicated situation, and that's what a lot of us do research on, is trying to understand the exact nature of these particles. Sometimes they're what we call internally mixed. And so what that would mean is that you have a particle, maybe its core is a sea salt or mineral dust, but then it has a coating of something else. Or potentially you have two types of particles coming together. Here I just draw sea salt and maybe something else sticking to it. And so we want to understand how these particles react with the gases in the atmosphere, how they influence climate. And so here's a real-life example of what a complicated particle may look like in the atmosphere. And we get this picture from transmission electron microscopy, which I call a really expensive microscope. So here at the University of Iowa, we have one of these. It's about a $1.2 million microscope, and we were able to buy that with funds from the Carver Foundation, so we can get detailed information about these particles, what they look like, what they're made of, so we can better understand their properties. So one of the reasons why we want to understand their properties is that these particles influence climate. We know already that CO2 causes global warming, and as Dan Reed said, we know that very, very well. But what do the particles do? And how do they influence this whole idea of climate forcing? We like to talk about this in terms of this unit of watts per meter squared, and I think Charlie Stainer may touch on this a bit in his talk, which he'll give next. And so we want to understand what the particles are doing. Now, why do particles influence climate? Well, they have two effects. We call them the direct versus the indirect effect. The direct effect is just that these particles can scatter and absorb solar radiation. So, you know, you have poor visibility on some days when there's a lot of particulate matter in the atmosphere. That's because they're scattering some of the light. So here we have the sun, here we have the particles. Some of them just scatter the light away. Some of the particles, like these darker ones, these black carbon particles, can actually absorb the sunlight. That can give rise to a warming effect. When they scatter the light away from the Earth's surface, that gives rise to a cooling effect. So these particles play a role in climate, but they can play it in a couple of different ways, cooling or warming the climate, depending on exactly what they are, and that's why we use this very expensive microscope to study them. These particles can also nucleate clouds. That's called the indirect effect. So here I have a particle. If it goes in the atmosphere where you have supersaturated water vapor, it can spontaneously nucleate a cloud. And here at the University of Iowa, in my lab, we can actually do studies of cloud condensation using a small cloud condensation spectrometer, so we can say something about how particles influence cloud formation. Once you have a cloud, that covers the Earth, and that gives rise to less solar radiation incoming to the Earth's surface. So we can think of the Earth's atmosphere as a complex chemical reactor. Okay, I'm a chemist, and so here's my vision of the atmosphere. So we have that globe, and now I've put it into a beaker where you have a lot of different emissions going on. Some of them are natural from vegetation. We have wave action, and we have this whole thing called mineral dust. And what's shown here is a dust plume from Africa. This is the coast of Africa right here, that makes its way all the way to the Florida Keys, where it can nucleate clouds in the Florida Keys. So it's truly a global environment in which we live. Dust storms in Asia will make their way all the way to Iowa. That's been followed by my colleague Greg Carmichael and his modeling group. So these are complicated, they impact climate. The other thing I want to say, here's some more satellite images. Here's Africa right over here. Here's the dust storm. Here's you can get a lot of great images from NASA and NOAA anytime. Any of you can get on the web and find a dust storm here somewhere in the globe and track it on a daily basis because of these remote satellites that we have now to track these types of things. There's also a lot of stuff is coming from Asia, is how I'll put it. We have a lot of dust storms. We have a lot of industry going on. This is a dust storm that happened in China, April 7th versus April 8th. And so we can see, depending on the given day, that visibility can be very different depending on the particulate matter. Here's an example in Seoul, Korea, showing a high particulate matter day. Here's a woman, she literally put a plastic bag around her head to avoid breathing in the particles. And I got this from the CNN website. And so you see that there's a lot of particulate matter in the air. And one of the problems is that these particles can impact health. For example, mineral dust particles can actually even carry microbes associated with them. So there's a climate effect, there's a health effect. And so we really need to understand these in much greater ways. So today, what I want to do is show you a video to describe some of the stuff that we've been doing. You'll hear a repeat of some of the concepts I talked about already, but basically just trying to get you to understand that, start from the beginning, Okay.
I feel like we're making a difference in people's lives by better
It's new science. I think it can hopefully change the world.
As cures for different types of cancers.
Understanding of the process of protein folding.
That's chemistry. That's a chemical reaction. I can help show.
I'm Vicki Grassian from the University of Iowa, and the Creative Advances in Environmental Science and Technology Award is for work that we've been doing for about the last 15 years, trying to understand the role of particulate matter in the atmosphere. The atmosphere is a mixture of gases such as oxygen and nitrogen and carbon dioxide, but also it contains a lot of particulate matter. This is small particles in the atmosphere that you can't even see, and we're focusing our attention on things that are described as mineral dust in the atmosphere. So if you think about a dust storm, we're interested in understanding the particles that get into the atmosphere from these dust storms and trying to understand how they impact the environment, how they impact human health, how they impact even climate. It is clear that human activity can change and increase the amount of dust in the atmosphere through land use, a more arid environment, a drier climate. These particles, they undergo what we call long-range transport. That is, they get miles and miles away from the source, and that will change the incoming solar radiation, that is the incoming sunlight. And the reason being is that these particles can scatter sunlight away from the Earth's surface back out into space. So we know about greenhouse gases and how they cause global warming, and now we're trying to learn more about how particulate matter plays a role in the Earth's climate. These small dust particles can play another role in climate in that reactions on the surface of these dust particles can either destroy greenhouse gases or can form greenhouse gases. Very recently in my laboratory, we determined a mechanism for the formation of nitrous oxide, a greenhouse gas that had not been previously observed. In fact, it's thought that nitrous oxide might even be a more powerful greenhouse gas compared to carbon dioxide. So these kinds of studies are important, so again, so that we can better understand sources, sinks, very important molecules, greenhouse gases, such as nitrous oxide in the atmosphere. Particles are known to play a role in respiratory disease. So it's well known that if there's days in where you have high particulate matter in the atmosphere, that the number of emergency room visits, for example, goes way up. Particles can impact the pulmonary system, it can impact the cardiovascular system, and so it's really important to understand the nature of these particles and how they interact with the human body. So we tried to work really hard to tie our laboratory studies, where we have a lot of control, and help understand what's being measured out in the field. So when people do field measurements, it's very complicated. They have no control over the variables. Sometimes it's difficult to say what exactly is going on. So in our laboratory studies, we're able to control the variables, and hopefully we're able to help people better understand the field measurements so we can better understand the Earth's atmosphere. We're also trying to help in terms of providing the data that is needed to put in atmospheric chemistry and climate models. It's important to have predictive models when we talk about the environment. And the reason being is that we want to be able to put in controls that make sense. And if we don't understand the fundamental processes and they're not in the models, we won't be able to predict whether decreasing emissions of this particular gas or of these types of particles will really help the situation in terms of less pollutants in the atmosphere, in terms of global climate change. So we really need to have that fundamental data in the models so they can give us scenarios that will help us understand what's going to happen years out. So I think that we've made a lot of progress in the last 10 to 15 years on what we do know about particulate matter, but I also think we recognize that a lot more work needs to be done. My own work is focused on mineral dust, but there are other particles related to organics in the atmosphere. Their composition is poorly understood. Their role in the environment is poorly understood. We have soot, and that also needs to be better understood in terms of its impact on human health, on climate, all the things that we've been talking about. Understanding the environment is very important, and I think that the research that we're doing is playing a role in better understanding the atmosphere, in better understanding atmospheric chemistry, better understanding climate, better understanding the role of particulate matter in atmospheric chemistry and climate. I feel like we're making a difference in people's lives by better understanding the environment. What's more important than that?
Okay, so that was the American Chemical Society put that video together after I won the Environmental Science and Technology Award. And pretty much that just sort of summarizes some of the things that I was telling you when I started. Particulate matter is also important in the atmosphere in terms of a number of different reasons, climate, even human health. And it's really important to understand the fundamental basis. So what I'll do now is I'll stop and I'll turn this talk over to Charlie Stainer, who will tell you more about climate change and this whole idea of climate forcing that I mentioned in my talk.